In this lesson on logarithmic functions and their graphs, our goals are to rewrite logarithmic expressions as exponential expressions and vice versa, evaluate logarithmic expressions with and without a calculator, and graph and translate a logarithmic function. A logarithmic function is simply the inverse of an exponential function. This can be defined as the following. Log base b of y equals x, if and only if b to the x equals y. This relationship will become important for the rest of the lesson. Think of the graph of the exponential function y equals b to the x, as shown here. You can recall that x can be any real number, but y can only be greater than 0. This is due to the horizontal asymptote that occurs at y equals 0 for the function y equals b to the x. These same limitations on the variables are true for the logarithm function as well. This means that the input, in this case y, must be greater than 0, and the output, in this case x, can be any real number. So let's practice a few problems by rewriting logarithms as exponents. I like to use the loop trick to rewrite logarithms. Look at log base b of y to the x. To use the loop trick, you'll start at the base and loop around to the x and to the y. So we'll have b to the x equals y. So using this, we'll solve example 1. We're going to set each one equal to x. So we'll have log base 5 of 125 equals x. Using the loop trick, we'll loop from 5 to x to 125. We'll have 5 to the x equals 125. We can rewrite 125 as a power of 5. This will give us 5 to the x equals 5 cubed. And since we have like bases, we can see the exponents will be equal. This tells us log base 5 of 125 equals 3. Let's try the next one. We'll set it equal to x, use the loop trick, and we'll end up with 7 to the x equals 1. Now we know with exponents, anything raised to the 0 power equals 1. This means our x equals 0. So log base 7 of 1 equals 0. This is true for all logarithms. With all logarithms, whatever the base, the log of 1 is going to equal 0. So this is true for all logs. Now let's try the next one. We can use the loop. Equals x. And we'll have 1/3 to the x equals 81. We can rewrite 81 as 3 to the 4th. And we can rewrite 1/3 as 3 to the negative 1. This leaves us with 3 to the negative x equals 3 to the 4. So we can see that our x equals negative 4. So log base 1/3 of 81 equals negative 4. Now let's try the last one. Using the loop trick, we have 8 to the x equals the square root of 2. We can rewrite this as 8 to the x equals 2 to the 1/2. And now we can rewrite 8 as a power of 2. So we'll have 2 cubed to the x equals 2 to the 1/2, which leaves us 2 to the 3x equals 2 to the 1/2. And now we can work with just the exponents and have 3x equals 1/2, divide by 3, and we'll have x equals 1/6. So this is working with logarithms that have bases of 8, 7, 1/3, and 5. They all have numbers. But there are two special logarithms that can be written differently. A logarithm with base 10 is called a common logarithm, and is written as log of y. A logarithm with base e is called a natural logarithm, and is written as ln of y. You can recall base e from previous lesson as an irrational number similar to pi. Now, knowing this, let's try the next examples. We'll set this equal to x, and we know that it is base 10 because it is the common logarithm. So we can write in 10 to help us see it, use our loop trick, and it works similar as to the other problems. We'll have 10 to the x equals the fourth root of 10, which gives us 10 to the x equals 10 to the 1/4, and this means x equals 1/4. So log of the fourth root of 10 equals 1/4. This next one is similar, except now we have the natural logarithm, which is base e. We can write it without the base, but to help us use the loop trick, we'll write the base in. So we have, using the loop, e to the x equals 1 over e, which we can rewrite as e to the x equals e to the negative 1. And here we can see that our x equals negative 1. Not too tricky. Now, there's one more useful consequence of this relationship, this inverse relationship, and that's the following. B raised to the log base b of m equals m, and log base b of the quantity b raised to the m also equals m. So let's use this to solve the following. We have log base 6 of 6 cubed. Here we can use the log base b of b to the m equals m property. So this looks like log base 6 of 6 cubed, and we can see our m is 3. You can still do this the way we did earlier with the loop trick by setting it equal to x. Log base 6 of 6 cubed equals x. Loop it around. We'll have 6 to the x equals 6 cubed, and we can see our x equals 3. That means log base 6 of 6 cubed equals 3. Now let's look at the next one. Here we have our common logarithm, so we know our base is 10, and we can also use the log base b of the quantity b to the m equals m property, because we have our log base 10 of 10 to the 5th, and we can see this equals 5. Now, let's look at some with exponents. Here we have e raised to the ln of 5. Remember, this is base e and can be written as e to the ln of e, ln base e of 5. And we can use the b raised to the log base b of m equals m property to see that we get 5. Here we can also use the loop trick, but in reverse. The way this works, we'll set it equal to x. We'll use our loop, but now we want to use log. So we'll have a log base e, so we know this is our base, log base e of x equals ln of 5. Now we know log base e is the natural log. So we'll have natural log of x equals natural log of 5, and we'll be left with x equals 5. Notice this is the same answer we got using the property. Now our last one is similar to problem C, and we can use b raised to the log base b of m equals m property. So of 8 to the log base 8 of 7 will equal 7. The loop trick can also be used on this one, but I'll leave that to you to practice. Now, let's look at how to graph some logarithmic functions. We can rewrite this first one as 3 to the y equals x. and choose some y values and solve for our x values. So we'll make a table, and we'll choose some easy y values to work with in this equation. We'll choose 0, 1, and 2. So 3 to the 0 equals 1. 3 to the 1 equals 3. And 3 squared equals 9. So these are the points we have. So now we can plot these 3 points. We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have the point 1, 0, the point 3, 1, so 1, 2, 3, up to 1, and the point 9, 2, which is 9, up, and 2. We also know that since the input of this here can only be greater than 0, and we also know the output of an exponential function is always greater than 0, we're going to have a horizontal asymptote, vertical asymptote at x equals 0. Now we can sketch our function like so. The next one is similar. Note this is the natural logarithm with base e, so we can rewrite this as e to the y equals x. Well, now we'll have a vertical asymptote of x equals 0 at x equals 0 because the output of a logarithm is always greater than 0. Or output of an exponential is always greater than 0. So we can make a little table, but since e is a harder value to work with, since it's irrational, we'll just use the y of 0. We know that'll equal 1, so we'll have the point 1, 0, and it's going to look similar to this one since it's still a logarithm. It'll follow this basic shape. We know it must be greater than 0. Now, let's move on to the next examples. Here we can use our transformations that we learned in Unit 1. We know what a parent function looks like from this equation from above. Notice we have log base 3 of x, and we're just applying some transformations to it. The minus 3 on the inside of the logarithm function tells us to move 3 to the right. So we'll move right 3. And then the plus 1 on the outside of the logarithmic function tells us we need to move up 1. So our asymptote will move 2 since the domain is now 3 to infinity. So we can make a few lines here. We know our asymptote has moved to x equals 3. And we can move our other points over as well. So 1, 0 becomes 4, 0. 3, 1 becomes 6, 1. And our function will look something like this. Now in the next one, we know our parent function for this is y equals ln of x, just like above. So we know it's going to start looking like this. Now the negative inside the logarithmic function tells us we need to reflect over the y-axis. So our asymptote will stay the same because we are not moving horizontally. And our point at 1, 0 will reflect over the y-axis and become negative 1, 0. Now our whole function will flip from one side of the graph to the other, so our logarithmic function will now look like this. Now for the last one, we'll have the parent function again is log base 3 of x. But we'll need to factor out a negative before we can determine our transformations. So if we factor out a negative from inside the logarithmic function, we'll have y equals log base 3 of negative of the quantity x minus 2. This means when we apply our transformations, we'll reflect over the y-axis and move right 2. Since we now have a negative here, we know we'll have to move right 2. So, taking the points we have from the original, we're going to reflect over the y-axis and then move right 2. So this point, 1, 0, becomes negative 1, 0, and then back to 1, 0. The second point will reflect to negative 3, 0, and then move to negative 1, 0, or negative 1, 1, pardon me. Now our asymptote will move to the right 2. So here we have our new function of log base 3 of 2 minus x equals y. And that is it for this lesson.